Sweet. Cool. So first things first, do you guys have any questions about U-substitution or anything along those lines from maybe last week or so?
Certain intervals that are difficult.
Yeah, Steve, we can totally do that. Which integrals are you talking about? And you guys can totally feel free to use your mics as well if you want. Because I can definitely go over some tricky trig integrals if you would like, or some more difficult parts questions.
Indefinite of sine cubed of 9x.
Oh yeah, we can roll with that. Let's see. Let's see. We're going to spotlight for everyone.
Oh, nice.
Yep. Okay, so the indefinite integral of sine cubed of 9x dx. So we can go about this guy in a number of different ways. What I would suggest doing is by breaking up this sine cubed into multiple versions of sine or cosine using your Pythagorean identity. So by Pythagorean identity, I generally mean that it's a sine squared of x plus cosine squared of x is equal to 1. And so we can pull out a sine squared from this guy. And just a regular sine of 9x. And then we can use our Pythagorean identity by saying that sine squared of x is equal to 1 minus cosine squared of x. So if we rewrite that, that means we have the indefinite integral of sine of 9x times 1 minus cosine squared of 9x dx. So once you get to this point, what I would suggest is most likely a U-substitution, because you don't necessarily want to get stuck in sort of the loop of Pythagorean identities. So let's set our U, let's set that guy equal to cosine. So a cosine.
The print is hard to read. I'm guessing it's the light.
X. Is that a little bit
Is there any way to turn down the light a little bit?
better? I can try to adjust the light.
Here.
It is. The phone.
I think it's just maybe that.
Is that a little bit better for you guys? Awesome, thank you.
Okay.
Cool. So if we have our U is equal to 9x, then our du, or our U is equal to cosine of 9x, our du is going to be cosine, that goes to
Negative
sign. So a negative 9 sine of 9x dx. And then we get that negative 9, or the 9 in front because of the chain rule. So then if we write this guy in terms of U, and that means that we are going to have, we're going to have 1 minus U squared, and then it's going to be a minus 1/9 du. And we got this minus 1/9 from this minus 9 over here. So all we did is we used a little bit of algebra, and so we just divided both sides by a -9. And that's how we got that -1/9 out in front. And we can also just pull this guy out in front because it's a constant. So then that means, I'm going to turn my autofocus off.
Yeah.
Come on, buddy. There we go. Cool. So that means that we are going to have -1/9 times the integral of 1 minus u squared du. Sweet. So then after that, it's not looking so bad. We can just apply it or take the integral as we would regularly. And so in that case, we are going to have -1/9 times what our integral is going to be, and that is going to be u minus 1/3 u cubed. And it's going to have a plus c on there because it's indefinite. And then let's plug in our u right now. So we can take this u is equal to cosine of 9x and plug it down. And then that becomes -1/9 of cosine of 9x minus 1/3 cosine cubed of 9x plus c. And then we can just distribute that in -1/9 in. So our final answer then is going to be -1/9 cosine of 9x. And this is going to become a plus 1/27 times cosine cubed of 9x plus c. As such. Does that make sense to you guys? Feeling a little better about that one? Sweet. Are there any other tricky ones that you guys have come across? Is there any tricky ones that you've come across? No? Sweet, no problem.
What happens if we do not have an odd number?
So if you have an even number, like if you have a sine or cosine to the 4th or to the 6th, something really, really big or just like not squared, then what you're going to want to do, so let's see, yeah, if sine or cosine both even. So we are going to want to use the half angle identities instead of like a typical Pythagorean identity. Sweet, and I can write those guys down. So at that point, you want to break it down. So say that you have like sine to the 6th of x. We can break that down into 3 sine squareds all multiplied together. And that's kind of what I would recommend doing to a point. And then you can equal each of these sine squareds of x. Let's see, that guy is 1/2 1 minus cosine of 2x. And so this is just one of them. You have half angle identities that work for cosine squared when sine x and cosine of x are multiplied together, or if you have like a cosine squared of x minus a sine squared of x. That guy's a little funky, and that's just going to be equal to cosine of 2x. Yeah, you can find all of these half angle identities as well as all of the every trig identity under the sun in your textbook or through sites like Symbol Lab or stuff like that. Those are always pretty helpful. Sweet, that's a great question. Yeah, and so some other tricks when it comes to these trig identities and trig integrals. So if your power of cosine, so say that you have like a sine to the m of x and a cosine to the n of x. If your cosine x has an odd power, you're going to end up at a U substitution, and you're going to want to use U equal to sine of x. And then if your sine of x has an odd power, then you're going to want your U substitution equal to cosine of x. And those are just really just useful tricks, really. Now, a lot of these tricks, if you guys come into contact with like using secant or tangent, a lot of those work as well. Would you guys like me to go over that? Sure, sweet, yeah, totally. Then go ahead and move to another page. So yeah, so this takes a look at the same sort of idea. So this is based on the identity that is secant squared of x is equal to 1 plus tangent squared of x. And so then really you're going to want to be looking out for where you have a secant squared or a 1 plus tangent squared or 1 minus secant squared even. But so if, again, you have a similar situation where you have secant of m of x times tangent n of x or along those lines. So if the power of secant is even, you're going to want to use a U substitution where you have tangent of x. And then it's not quite the same for when you're looking at the powers of tangent. So you want to look and see if the power of tangent is actually going to be odd. So if the power of tangent is odd, then let me see here. You want your U substitution equal to a positive secant. Sweet. Yeah. And then there are other identities. I would definitely recommend taking a look through your book or any sort of handouts that your professors give you guys. Let's see. I know that you guys have a homework assignment due tonight on these integrals or these kinds of integrals. Are there any sort of questions from the homework that you guys want us to cover? Are there any particularly nasty ones?
Indefinite integral of 14 times sine of 6x times cosine to the third of x dx.
Yeah, we can totally do that. Yeah, Zoe, great pick. Awesome. So then, yeah, so let's go through. Yep, it's going to be, let me move this up a little bit. So it's going to be the integral of 14 sine to the 6th, yeah, of x, and then cosine cubed of x dx. Sweet. So we are going to use the same sort of methods that we just talked about. And the first thing that I want to do is just move this 14 out in front, get it out of the way for now. So 14 sine to the 6th of x cosine cubed of x dx. And so here we see that we have an even power in sine and an odd power in cosine. So we know that we don't need to use our half angle identities. And so we can see that if we're looking for which one has the odd power, that our cosine is going to have the odd power. And so if cosine has an odd power, we're going to want our u eventually. Our u is going to be equal to a sine of x. But let's split this up and see how we can simplify what we have already. So we have an odd series of sine, or an even series of sines, and then an odd cosine. So let's break up this cosine into a couple different things here. So we are going to break this up into a 1 minus sine squared of x, which is going to be equal to a cosine squared of x. And then we're just going to leave a regular cosine in there as well. So that means that we can rewrite this as, let's see, I'm still on the page here. It's going to be 14. We're going to keep our sine to the 6th of x. And that means that we are then going to write this as quantity 1 minus sine squared of x, and then a cosine of x dx. And so, yeah, here you can see we have a ton of sines, we have one cosine. And so this is why it makes sense to use u as our sine of x. So let's simplify this a little bit more. Let's go ahead and distribute this sine to the 6th into this 1 minus sine squared. So we have sine to the 6th of x minus sine to the 8th. That's nasty. And then all of this times the cosine of x dx. So if we have our u equal to sine, our du is just going to be, thank you. Our du is going to be just a regular cosine of x dx, which we can see we have right there. So it's a really nice substitution, actually. And so I'm actually going to move over here. So now in terms of u, we can rewrite this 14. This is going to be, let's see, u to the 6th minus u to the 8th, and then just a regular du. So not too bad. Then we can go and evaluate the integral as we would just a regular algebraic integral. So that means that we're going to have 14 times, it's going to be 1/7 u to the 7 minus 1/9 u to the 9 plus c. I would recommend plugging in your u in at this point. So that way you have 14, 1/7 sine to the 7th of x minus 1/9 sine to the 9th of x plus c, and then going in with your 14 and distributing that across. Save the algebra for last. And then, so yeah, in that case, we're going to end up with 2 times sine to the 7th of x, and then we're just going to keep this as a 14/9 sine to the 9th of x plus c. And that will go ahead and be our final answer. Sweet. Thank you, Zoe. That was a great question. Awesome. Are there any other problems from the homework? Oh, that's one. Okay.
Well, off topic, but generally dealing with trig integrals that are a fraction like sine over cosine cubed, we would sub cosine almost.
Yeah, that's great, Steve. So yeah, remember that you can always rewrite if you have like a sine of x over a cosine cubed of x. Say again.
Move it off just a little bit.
Oh, yeah. So if we have a situation like this, and it really is the same as when you're dealing with any sort of weird fraction with powers, what I like to do is say that this is sine of x and then cosine to the -3 of x. And so when you have that negative in your power, that's really just saying that it's in the denominator of an imaginary fraction. 7.2 number 5. Yeah, of course. Yeah, so does this help, Steve? Or let me see. Yep, sweet, awesome. Yeah, then let's move on to 7.2 number 5. Give me just a second. Okay, cool. So this is see, I hope, am I on the right? Is it 7.2?
Yeah.
Oh, yeah, it is. Okay. So 7.2, number 5. A lot of the numbers that we have are probably going to be different. I see here that we have a coefficient in red, so it shouldn't change your answer too much, but just keep that in mind. So we have a definite integral that goes from 0 to pi over 2. That is going to be, in our case, of 13 sine squared. There's that 2 theta. Nasty. 2 theta and then d theta. So let's see. I would say, yeah, probably a half angle identity is going to be our best shot with this one. So half angle identity. And in this case, there is one for sine squared. So sine squared of, let's write it in terms of theta this time, is going to be equal to 1/2 times 1 minus cosine of 2 theta. So the only thing that's different here is that we already have a 2 theta in here. So that just means that the 2 will carry on and just become a 4. So if we want to rewrite this, that means we go from 0 to pi over 2. And it's going to be of 13 halves. Just going to go in and distribute that 13 to that 1/2 right now, times 1 minus cosine of 4 theta d theta. And so at this point, you can just go and take the integral as is. So I would restructure it a little bit before you do that. I would move this 13 halves out in front just for convenience. So 13 halves going from 0 to pi over 2 of 1 minus cosine of 4 theta d theta. That means that we're going to have 13 halves. That is going to be c theta, and then minus 1/4 sine of 4 theta. So we abide by the chain rule. And that part of the integral is for the product of the integral? Result of the integral.
Result, I would say.
So the result of the integral, that's going to go from 0 to pi over 2. And I would plug this in. I would evaluate with your bounds before you multiply by this 13 halves. So in that case, then you're going to have 13 halves. Let's see. So that is going to be pi over 2 minus 1/4 sine of 4 times pi over 2. And then minus 0 and actually just going to do parentheses, and then minus 1/4 sine of 0. Like that. So yeah, so this is of course all going to be, or sine of 0, yeah, it's still 0.
Yeah.
Yeah, so this entire side, all of this is just going to go out to 0. And so then we are just left with this guy over here. 4 times pi over 2, that's going to leave us with a 2 pi. So that is also 0. And so the only part that really comes into play is just this pi over 2 right here. So that's really all we have to multiply our 13 halves by. And so that means that the answer to our integral is going to be 13 pi over 4. And there you have it. Let's see, 19 sine squared.
So hers would end up being 19 pi over 4.
Okay, yeah. Yeah, so then, let's see, Yeah, so Hunter, in your case, yeah, you would just have a 19 instead of a 13, chances are. Awesome. Sweet. Any other specific questions?
Will there be one like this on the example?
Let's see. Because it uses a half angle identity, I'm not super sure. I know that you guys are definitely given Pythagorean identities, at least the one for sine and cosine. As for other things, I'm not sure if the math department really has that figured out quite yet. So that's a good question for your professor, just to give any sort of details about what else you need to memorize in terms of the identities, or if you need to memorize anything at all. They could just stick with giving you the sine and cosine, and then only having those on there. But I would say it's good to be prepared for half angle identities. There's only maybe like 4 of them. So I'd say it's good to be prepared for that. Oh, Emily, perfect. Yeah.
Get the half angles.
Yeah, if you guys get a formula sheet, maybe there will be the half angle identities on there. If one section is getting a formula sheet, in my mind, all of them should.
Yeah.
But yeah, if you guys are part of the larger group that goes through Calc 2 under Joy, then you guys should be good. You guys should be good to go. We'll give you what you need. Awesome. Let's see. So how do you guys feel about the later problems of your homework for tonight? So looking at like number 13 or 14.
It's probably on the side homework. So like 2 triggers, or 15 is weird graph problem.
Yeah.
Oh yeah.
Steve and I are on the same page. So yeah, so let's see. Looking at number
Just
14.
the illustrating part.
Yeah.
Next,
So
next one.
Oh,
15.
next one. Oh, yeah. Okay. So evaluate the indefinite integral. That's pretty straightforward. Illustrate and check that your answer is reasonable. Huh.
I think Mathematica that form.
Yeah, I would say maybe tackle it in Mathematica. So if it's asking you to graph both the integrand and so it wants you to graph the indefinite integral that it gives you. So that sine of 3x times sine of 6x times some sort of coefficient, wants you to graph that and whatever you get in terms of
14. Yeah, so basically you have to plot those on the same graph overlaid, and then just kind of match it up to whichever option is shown.
Yeah, it's really just looking for, I think, just 2 overlaid graphs, and then yeah, that really just looks like 2 overlaid graphs in all those options.
And it looks like your x bounds are just -2 pi to 2 pi. Or sorry,
just -2 to 2.
Or, yeah, you could do that as well.
I don't think it really matters
Just
as long
pi,
as it's a
yeah.
graph.
Yeah.
Yeah. Cool. Yeah, that one's a little tricky.
Yeah.
Oh yeah, there's the 53. Cool. Yeah.
Any other questions?
You guys have been great. This is fun.
Yeah.
Let's see. Cool. How did partial fractions go today? I know that you guys just started on that. Do you guys have any sort of questions? Let's see, what section is that? That's 7.
Possible to work through 7.2, number 6.
Yeah, totally. You can totally go through that.
I love partial fractions. I'm not gonna lie, one of those guys.
Well, you can handle that next week. Or no, not next week.
Can we please do an example for partial fractions?
We can totally do that, Emily.
Take that one.
Sweet. So it looks like number 6 is a tutorial.
So they're very specific in what they want.
Yeah.
So you may have it right, just not their version of right. So let's just kind of walk through that and see what
Yeah.
happens.
So let's see. I'm actually going to go ahead and start a new piece of paper.
Yeah.
And all sorts of trees tonight. Cool. So we start off with, this is the wrong pencil.
This paper's green, right?
So we have, in our case, the integral of 17 sine squared of x cosine cubed of x dx. So click here to begin. Oh, how friendly. Oh, what did it do? So the first one saying cosine squared of x is equal to blank minus sine squared of x. If it's just a blank like this, that's just going to be part of your Pythagorean identity. So in this case, it's just going to be a 1. Not too bad. Let's see.
Oh, that's gonna be really
So then, oh wow, yeah, it just kind of jumps right in there and it gives us a new coefficient. Great. Cool. So they go ahead, yeah, so they change this, using this identity, they change this cosine cubed into, that's going to be a 1 minus sine squared of x times a cosine of x. And so then it goes ahead and distributes and breaks it up into 2 separate integrals. And it does that by, so 17 sine squared of x, 1 minus sine squared of x. It breaks it up into 2 separate integrals because we have this minus sign right here. And so then that means that we'll get this 17 sine squared. That'll distribute to the 1, and it'll also distribute to a sine squared right there. So you'll have the integral. It actually distributes the cosine as well. So you'll have, yeah. So you'll have 2 integrals. The integral of 17 sine squared of x cosine of x dx, and then minus the integral of 17 sine to the 4th of x cosine of x dx. Yeah. So then, let's see, after step 2, maybe just step 3. So since cosine of x is the derivative of sine of x, then we have sine squared of x cosine of x can be done by substituting. So yeah, just like we covered a little bit ago, or I guess this just looks directly at this guy right there. So when our cosine is odd, let's see. I mean, with this one, you don't even have to think about it that too terribly badly. We know that we are going to have a lot of these, and we need our du equal to this guy right here to make it work out nicely. And so then our u is going to be a sine of x, and our du is going to be equal to the cosine of x dx, like we need it to. Pick up nicely. And so that is focusing specifically on this section right there. Then after, okay, yeah. So it just takes it one step at a time, or one integral at a time. And so that's, I'm guessing this tutorial is pretty long. And so it'll cover this guy. Then it wants you to go ahead and integrate this one. And then immediately as part of the same step, go and apply the same sort of techniques to that guy right there. Or actually, no, not yet. Yeah, so from this, you should end up with, let's see, the integral of a 17 u squared du, which is not too bad. You can evaluate that just using the same techniques as some, like a regular algebraic integral. And then, let's see. Yeah, and so then it says in the next step, you want to use, so let's see, so Emily, is there a certain trick for picking out which values to use for the u for these problems? Yeah.
The odd number, right?
Yeah, so see, that goes back to choosing, that goes back to this bit down here at the bottom. So when you have a lot of these like weird integrals with really high powers that we're not used to seeing, you need to look at if the powers are even or odd, and that'll tell you what to use your u as. So in the case of the problem that we're going through now, we have really just cosine to the 1, which counts as being odd. So we use our u as sine. And then if sine of x would have an odd in a different problem, we would use cosine for our u. And that's simply because when you have like cosine to the 5th of x, you can break it up into 2 different like cosine squareds, and then just a single cosine. And so this cosine that'll be tacked on at the very end, this is what you want your du to be equal to at some point. So if it has an odd power, it'll end up being equal to your du. So that means that your u needs to be the other one. Yeah, no problem. Sweet, yeah, so continuing on with the guy that we have here, we have the same sort of situation where we have a cosine to the 1. So our u is going to stay as sine of x. Du becomes that cosine of x dx. And then you're going to have minus the integral of 17u to the 4th du. And you can evaluate that using algebra as well. So then when you're combining these guys together, you can really just make sure that you have the result of this guy. And then you just have to make sure that this minus gets carried down. So it's the result minus the result. And that'll give you your final answer. And then just don't forget that plus c. And that should be good. Let me just double check and make sure that it doesn't do anything weird. Nope. Yep, that's how number 6 ends. Cool beans. Let's see. Number 6. Let's go ahead and run through a partial fractions example. Do you want to run through that, David?
Yeah.
Cool. So David, the other coach I have here, is going to start running through this guy. Let's see, which example or which page?
Page 533, example number 1. So that involves long division.
Spicy.
And then there's another one as well. And if we have time, I will get to it, but it is example number 4, which starts on page 536 and it's on page 537.
Well, you said 532 for the first one, right?
Yeah.
Cool. Sweet. Take it away, David.
Alrighty, so if you see something along the lines of, of an integral of, we're going to do x cubed plus x over x minus 1. So in this case, the power in the numerator is higher than the denominator, in which case we can't do partial fractions just yet. Okay. So in order to start this problem, we have to do long division. So the first step is you take what's on the bottom, you put that outside of your little, I guess, boot thing right here. That's how I learned it. So then we've got our x cubed plus x in there. So x times what is x cubed? Well, that would be x squared. Put that here. And then we got x times x cubed. And then we're going to have a minus, or sorry, a plus x. Oops. Plus x right here, and that just comes from the 1 and the x here. So then we're going to do the x cubed. Jesus. Sorry, I'm wasting all of your lead, Sydney.
That's okay.
So we got x cubed. So x squared times x is x cubed. So that goes down here, and we're going to subtract all that. Minus x squared. Now it's going to give us, so these cancel out, and then we're going to get an x squared, because that becomes positive since the two negative signs cancel out. So we get the x squared, and then plus this x just comes right down. Okay, now we do it again. So we get okay, so then we get x times what? Where am I? Sorry, I'm getting backed up here.
Yeah.
I got the x cubed. We're down here at x squared plus x.
It's just times and x.
Yeah. So then we get this x squared times this x is going to be an x cubed, or x squared, sorry. An x squared, and then we get the -1 times this x equals a negative x. And once again, this is all subtracted. So then we're going to get these x squareds will cancel out. This x right here becomes positive, so then we get 2x. Okay, so then we got 2x, and then
So then next we need to look at what will go into this 2x, what we can multiply by our x minus 1 to get that 2x. So in this case, it's going to be a 2. So
Yeah.
that's where we get a plus 2 up in our quotient.
and then that's just going to be a 2x down here from this 2 and this x.
And then,
And then
minus 2.
-1 times 2 is -2. That's of course subtracted, and then these two x's will cancel out and we get a 2. And this 2 is our remainder, which just then goes above the x minus 1. So as a result, we get, so this turns into the integral of x squared plus x plus 2 plus 2 over x minus 1.
Should bring some 0.7 pencils next time.
Oh, you have 0.5?
Yeah.
I can use my own if you like.
It's fine. It doesn't matter.
dx. Okay. So then after integration, we just get x cubed over 3 plus x squared over 2 plus 2x. And then this plus 2 times the natural log of the absolute value of x minus 1 plus c. I'll isolate that from everything else. And that would be our answer. So that's long division. Now, if you don't see that, and let's say you get something along the lines of the integral, just try and move this a little bit, of 4x over x minus 1 squared times x plus 1 dx. So for this one, we need an a over x minus 1 plus b over x minus 1 squared. So if you have some term squared, cubed, or higher, each of those terms needs its own letter or its own constant. So if that was x minus 1 cubed, you would have a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. In this case, we just have x minus 1 squared, so we'll stop at b. Then we just have plus our c over x plus 1. So next step is we take our a, and then we do a times, scoot up a little bit. I don't know why I'm always writing off to the side as well. So a times, we need an x plus 1 and one more x minus 1. So how I got this was I need a to be multiplied by everything that is not under here. So basically here we have an x minus 1 times an x minus 1 times an x plus 1. Well, a has that x minus 1 right here, so we just need the x plus 1 and the x minus 1 that remain. Plus b, so since b has that x minus 1 squared, that just needs to be multiplied by our x plus 1. And then that's going to equal the 4x up here. So now we have to solve for a and b, and the easiest way to do this is make each term cancel out one at a time if we can. So if we set x equal to 1, then this term here is just 0. So all of this goes to 0. So that would mean that we have 2b equals 4 times 1 is 4. So b is going to be 2. And then for x equals -1, that makes each of these terms become 0. So we actually can't use that one. So in this case, what we could do is if we set x equal to 0, we get, so that's just a 1 times a -1, so we get -a. And then for b, well, b is 2, so we have 2 times 1. Which is just 2, so -a plus 2 equals 0, and we get just a equals 2. So now we have, oh, I forgot my c term from the get-go. Oh, apologize. Were you what?
I didn't want to stop you. We're on the roll.
You could have stopped me right in my tracks. Okay, so we got, so because I forgot my c term and I was on a roll, all of this, I apologize, is actually wrong. That is invalidated 100%. Ignore the past about 2 or 3 minutes of work.
Omit it from the register.
Yeah, does not exist anymore. So x minus 1 squared. And I just got that because c has at x plus 1. So we just needs the x minus 1 squared. And then that all equals 4x. Okay, so we're going to have to start over now. But if we once again set our x equal to 1, then we're going to get 2b equals 4, and b in this case is actually still 2. So then what we can do is if we set x equal to 0, Do it over here. Make that sit at an angle, I'll start writing straight. So if x equals 0, oh yeah, that's a lot better. Maybe it is. We're gonna get, so that becomes 1, becomes a -1, so we get negative a plus 2, b is 2, so we're gonna get negative a plus, and that's just gonna be 2, and then c just, yeah, so plus c, because that's a -1 squared, which makes it positive, equals 0. So that's equation 1. Now we have to set a x equal to something else that is not 1, 0. We could use -1, right? I imagine. So if we set x equals to -1,
Yeah.
yeah, that's not going to cause any problems. So we have b goes away, a goes away, c does not. So we have, so it's going to be 4c equals -4, right?
+4.
But
A
a is
minus
negative.
1 minus 1 is -2 squared. +4. C is equal to +4.
4c, x is -1, 4x times -1 is -4.
Oh, yeah.
Okay, so c is -1. So then we can take this, throw it up here and solve for a. So then we get -a plus 2 minus 1 equals 0. And if we solve for a is just going to be, what do we got here? A positive 1? 2 minus 1.
minus 2.
The negatives cancel out.
Yeah, +1.
So a is 1. So then what we do is take our a, our c, and our b. We get 1. I'm going to buy you some lead. 1 over x minus 1 plus 2 over x minus 1 squared plus, and then c we said was -1. So just going to take that as a minus then. It'd be -1 over x plus 1. Integral dx. So this looks a lot easier than what we started with up here. So now we just get, for, I'm going to call this term 1, term 2, and term 3. So term 1, that's just going to be the natural log of the absolute value of x minus 1. And then term 3 is just going to be minus natural log absolute value of x plus 1. And then for term 2 here, that's going to have to be a U-substitution. So that's just going to go to 2x minus 1 to the -2. And then if u equals x minus 1, du is just dx. So that's just going to be 2 times u to the -2 du. And then that's just going to be 2u to the -1 over -1, which is just -2 over x minus 1, because that was our u, and that becomes -2 natural log of x minus 1. Let's get up. Let's get up. Okay. So the final answer is natural log of x minus 1, and that's the absolute value of x minus 1, minus 2 times the natural log of x minus 1, minus the natural log of x plus 1, plus c.
Sweet. Awesome. Thanks, David. Does that help? Does that help with your understanding a little bit, Emily?
Yes, thank you so much.
Yeah, absolutely. No problem.
I do have one question though. So in the U sub part, if you had like, let's say 3 over x minus 1 squared, would that be like -3 natural log x minus 1? Like, is it always going to be that same pattern?
It should be, yeah. I would, definitely always double check.
wait.
But if you were gonna, you mean like a 3 in the place of the 2
I
in the
did-
numerator?
I did 2 integrals. I just realized that.
What do you mean?
I did that integral right here, and then I made the natural log. You see what I did?
Oh, yeah.
So all I gotta change is just
Good night.
2 over x minus 1.
Okay.
And don't break your pencil lead. Okay.
Good deal. Yeah, sorry about that little bit there.
Yeah, sorry.
Oh, no, it's okay.
Yeah, so yeah, it should follow a lot of that. This is a super standard sort of partial fractions problem. And you're just gonna end up with a lot of natural logs.
Okay. That makes sense. Thank you so much.
Yeah, no problem. And we're actually gonna call it here tonight. So have a great rest of your night.
Thank you, you too.